Today, we want to grab one of our old problems, modify the numbers, and add some new problem to it. Specifically, we're going to take a hemispherical bowl, put some stuff in a bowl. This is a pool. It's 10 meters, 12 meters radius. So we got this hemispherical pool, and we're going to partially fill it with water because that's the interesting part of the integration. And then we're going to calculate volume like we have done in the past, but we're going to add our new problem to it. Our new problem this week has been work is equal to force times distance. So the second part of this problem is find the work done in pumping the water over the edge of the pool. Now, the interesting thing here is not only does the volume have some continuously variable stuff, the radius is continuously variable from the 0 down here up to the radius of whatever it is when we're 10 meters deep. But other things are variable. Work is equal to force times distance, but distance is also going to be variable for each part of this water. Note that at the very top of the water, this slice of water, the surface, only has to go 2 meters to get out of the pool. That top surface of the water only goes 2 meters, whereas this bottom slice down here has to go a full 12 meters. So one of the variables that's going to show up in our calculation is the distance. We're going to write work is equal to force times distance. And that distance is going to be variable because up here, 2 meters, down here, 12 meters. So distance is variable. Other elements that we're going to need, we have volume, and work is equal to force times distance. Volume is not going to cut it. I'm going to need to take the volume. It's going to be some number of cubic meters. I'm going to need to multiply by the density of the water, 1,000 kilograms per cubic meter, to turn our volume into a mass. And then we'll need to multiply by gravity to turn our mass into a force. So that will give us newtons and meters. Those will be the things that we need. First, let's look at this volume problem. This is a volume problem that we've done in the past. The volume of the slice is pi r squared times x because this is a hemispherical pool, so that slice represents a circle. So the slice represents a circle. We're looking at it from the side, so we only see that cylinder, pi r squared times h. But if we look at it from the top, we will see a whole circle. It won't have a hole in it, it'll be filled in. There, I'll fill it in. We're going to do the same thing what we've done in the past. I'm going to use a right triangle to get a relationship between a variable going up and down and a variable going side to side. So my right triangle doesn't go from the surface of the water because that's not going to give us a consistent radius of 12. We have to go from the center of our hemispherical bowl to get a consistent radius of 12 meters. So now we've got a right triangle with a constant hypotenuse of 12 meters. 12 meters here at the top of the bowl. Hypotenuse is 12 meters at the surface of the water. Hypotenuse is 12 meters at the generic slice I picked in, and hypotenuse is 12 meters when we're down here at the bottom without even a triangle to speak of. We need to define our variable x. We need to define our variable x, and there's nothing to stop us from making x the most convenient thing in this case. So x will be the distance from the bowl to the slice. So make x the leg of that triangle, then x squared plus r squared equals 12 squared. So now we have x squared plus r squared is 12 squared. We want to know what the radius in the volume of the slice. I need to know what the radius is in terms of the delta variable, delta x. So r is the square root of 144 minus x squared. So this tells us that R is the square root of 144 minus x squared. Now we've got our expression for the volume of the slice. The other thing that we have to do is decide, the other thing that we've already decided actually, is the values of x over which we are going to be integrating. We want to integrate where there is water. Once we decided where the x was, we decided that the top of the bowl was where x is equal to 0. And the bottom of the bowl is where x is equal to 12. So at the surface of the water, x is equal to 2. So I want to integrate where there's water. So that's why we're integrating from 2 to 12. That's the 10 meters deep water, the 10 meters of water that we integrate from 2 to 12. This is all because we decided to put x where we put it. So the volume of the slice, or the volume total, I'm going to factor out the pi. I'm going to simplify the square root of 144 minus x squared squared to just 144 minus x squared. My discrete delta x becomes a continuous dx. And we integrate over all the x values where we have a slice of water from 2 to 12. That's the 10 meters of water that we want to integrate. When I say want to integrate, I mean grab our calculator and have our calculator integrate for us. So I will math 9, 144 minus x squared with respect to x from 2 to 12. So 2600 over 3, that's weird. Let's just multiply by pi. 2722.71. 0.7 for 5 significant figures. This is calculating the volume, so we're going to have cubic meters. Yes. Oh, yeah. I'd have to change multiple 2, so I'll just change the 9 to a 10. Thank you. I'll edit that in post. I'm just kidding. I wouldn't edit that. Yeah, there'd be more 2s to change, and there's only one 9 to change. So thank you for pointing that out. So we got 2,722.7 cubic meters. Now note our cubic meters goes all the way back to the volume of the slice. Our radius is in meters, and that's getting squared, so we get meters squared. Our delta x is where the third meters comes from. So meters times meters, cubic meters. We can also just assume that we've got everything lined up and know that we're calculating the volume and just write meters cubed. That would be the confidence move. So part 2 of this problem is to calculate the work done in pumping the water just to the top edge of the pool. So all these parts, the parts that we have to move are all different sizes. So there's variation in the volume. The density is nice and constant, so at least we got that. But the distance is also variable. So in the work part of the problem, the surface of the water only needs to go 2 meters. The surface is 2 meters from the edge of the pool, but the bottom of the pool is 12 meters from the edge of the pool. So that means that distance is variable, is going to be a variable in this problem. Distance is going to be a variable in our integral. So we know that work is equal to force times distance. We know that distance is one of the variables in our integral. We know that force is also going to be one of the variables in our integral. The slice of water at the surface is much bigger than the slice of water at the bottom of the pool. So that's going to mean more force at the surface than there is at the bottom of the pool. So for force, we need to do the mass times gravity. So force is mass times acceleration here. Acceleration is due to gravity. And we're on Earth, so 9.8. So force is mass times gravity. So work is mass, gravity, and distance. We have an expression for the volume of the water, so we need the density to get the mass of the water. So the mass of the water will be density times volume times gravity times distance. Density is our constant, 1,000 kilograms per cubic meter. Volume, we have an expression for. Gravity is constant because we're not moving things so far that gravity will be different. And distance is a variable. The convenient thing for us is that the distance that the slice has to go is just the variable that we're using. So this slice needs to get to the edge of the pool. That is the distance from the slice to the edge of the pool. So let's just start filling in all the stuff that we need for the work of the slice. The density of water, 1,000 kilograms per cubic meter. The volume of our slice is pi times the radius squared times delta x. Gravity is a constant 9.8. meters per second squared, and distance we can write as x, since the slice the distance from the slice to the edge of the pool is x. Here are all the pieces that we need. These first three pieces are going to give us force. So I got kilograms per cubic meter times cubic meters times meters per second squared times meters. So this is going to give us newtons and meters. It will give us kilogram meters per second squared times meters. We need to integrate where there is water, and the water is still from 2 to 12. So the total work well, I'm going to factor out 1,000, a pi, and the 9.8. So I need 9.8 thousand. I factor out a pi. I'm going to simplify my expression. This square root of stuff squared is just stuff, and it's multiplied by x. So I have a factor of x, and then the 144 minus x squared. Our discrete delta x becomes the continuous dx. And we only want to integrate where there is water, and there is water from x equals 2 to x equals 12. All that's left now is to grab our calculating machines and calculate. So I need the math 9 of x and 144 minus x squared with respect to x from 2 to 12. So 4,900 times 9,800 times pi. So we get lots 1.50. I'm not going to be able to count these. I'm not going to be able to count all the digits because it's too small. Oh, I'll just be able to do it when I'm writing. 1.5085459, so 6 times 10. Oh, I do have to count them. Shoot. 1, 2, 3, 4, 5, 6, 7, 8. To the 8 joules. So it's going to take a lot of energy to do it. I don't know if this seems reasonable. I'm not a physics guy, so I don't know what 1 joule is supposed to do, much less billions of joules. There's also the question, could I just not take the volume and multiply by the average distance that it has to go? Take the volume find the mass of the water and just move the mass of the water the average distance. Since the mass of the water is just a constant and the work required is just a constant, yeah, we can just multiply that by the average distance that everything has to go. But there's all these averages, and to find averages, you have to add things up and divide by how much is there. And if we're going to add things up and they're changing continuously, we're going to be doing integrals anyway, because integrals are just how we add things up when those things are continuously variable. So can't we just use the averages? Yeah, that's what we're doing. How's everybody okay? There's all these calculations, and when students are good at calculations, we decide that they are good at math. And we forget that there's a whole intuition that goes along with it. And that's what we're trying to build. We're trying to build the sight, the perceptual twist, the vision. Trying to make you see something. Not just the calculation. The calculations just get in the way. That's what people dislike about math the most. We're trying to see something that's really cool. We're trying to look at this system that we've been developing to describe our world. And all the language that we need gets in the way. All right, so here's how we can incorporate, take our work and just add some more complication to it. Work is equal to force times distance. Just start making a bunch of the factors continuously variable. And you can get integration problems out of it. Speaking of getting integration problems out of things, here is the variation of this problem that is one of my favorite variations of this problem. Let's suppose that we sealed off the pool and then inverted it so that no water is lost in the process. Suppose that we've sealed off the pool and invert it so that no water is lost in the process. Do I have a blank page of this? The new question is, find the depth of the water in the pool. So the new problem is to find the depth of the water in the inverted pool. So we're still having a hemisphere. The hemisphere is still 12 meters in radius. What's going to happen is what was space at the top, at the widest part of the pool, is now going to be space at the skinniest part of the pool. And the new question is, how deep is this? What we want to recognize is that the answer is not 10. If I just filled up a cylinder and inverted it, it would just be 10. Because the cylinder is symmetric top to bottom. This pool is not symmetric top to bottom. So down here, it's a much wider space than there is up at the top. So all this water that had to be crammed into this space here has more room to spread out down here at the bottom of what is now the bottom of the pool. You can tell that I'm not going to be finishing this problem today because I'm about to write, show your calculations. And I'm going to say round your answer to 3 significant figures. So we want to find the depth of the water in meters, and I want you to round to 3 significant figures rather than 5. Once you figure out one way to figure out to solve this problem, you'll know why I dropped from 5 down to 3. Any questions about the form of this problem? All right. So this is the problem that we will talk about tomorrow. We'll talk about the volume of the water in this inverted pool. If there are no more questions, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.